Hi, everyone. We're going to wait just a minute before we get started. Check. All right. Is everyone able to hear me? Can you hear me? Okay, good. Usually I pop.
Yes,
You can
hear you, Professor.
Thank you. Okay. Usually I pop up and I didn't pop up, so I got worried. Okay. Thank you. Welcome everyone. Thanks again for making time out of your busy schedules. We're almost done. All right. Just a few things left. I really appreciate all of your constant questions, asking questions, and being responsive on your end. I hope that I've been able to be responsive on my end. We are near the end, but just so you know, if you do have questions, don't hesitate to reach out to ask, even between now and the final. I am available for office hours. Today, I want to go over the things that you really need to know for the final. That doesn't mean that there couldn't be possibly one question that's not in the slide set. I want to be clear, but I took the slides that you have already been exposed to, which is a lot, and reduced it to a more reasonable number and just kind of go over some of the main concepts in this class. I also put this PowerPoint already on Blackboard on week 4, just the slides, so you don't have to rigorously take notes during this. You're welcome to, or if you want to open up that slide deck while we're doing this, that's fine too. So I'm going to start off with the main themes that you should focus on, and then dig in a little deeper. So if you can only tune in for the first 5 minutes or the first 2 slides, that'll get you close as far as knowing what you need to study for. And then I'm going to go through the slide deck fairly quickly. There's about 50 some slides, but just to kind of give you a sense of what to focus on and what you maybe don't need to worry about for the final exam. Okay, so and then if there are any questions about assignments, the individual project, homework exercise 4, those kinds of things, I'm going to do that at the end if that's okay. That way we make sure we get through all this. All right, so here we go. So one of the most important concepts that is also one of the most easy ones to mix up is the logic of the null hypothesis. And one way to memorize what the null hypothesis is always that there is no association. In the case of means, it means there's no difference in between the means. And the reasoning behind this, and you're always probably thinking, why are we making this so complicated? It's meant to be somewhat conservative in that we are allowing enough evidence to accumulate based on probability to reject that null hypothesis. So you can equate it to the sort of innocent before proven guilty. But it does cause a lot of confusion. Thankfully, in your homework exercises and in the quizzes, but especially in your homework exercises, it seems like people are really getting this concept that the null hypothesis is 0 or no association. And then to reject that means that we do have enough evidence to say that no, they are not 0, they are not equal in the case of means. So just make sure that that logic is clear in your own mind. Correlation, I cautioned a few of you in your writing to avoid using the term correlation loosely, because it does have a more specific meaning within the context of statistics, specifically the relationship between two either continuous or interval variables. And just remind yourselves what it means to be a positive correlation, what it means to be a negative correlation, and also the fact that 0 means no correlation. +1 is perfect positive correlation, perfectly linearly associated, and -1 is equally as strong a correlation. It's just a negative or inverse relationship. So it's really easy to think negative values mean nothing or lower than, but it's the absolute value of the correlation coefficient that is important. So that's another concept that I think people often confuse, and that's why I'm putting that up here front and center. Do keep in mind that with these statistical tests, we're not out to prove anything or make a statement about causality. And even though we might, in the context of a regression model, start to portray it as if we're showing causality, to demonstrate causality requires a lot more steps. And there's different criteria, including showing a dose response and the study design itself and things like that. So just always make sure that we're always thinking in terms of association, not causation. Just wanted to make sure you remember that. The difference between a population and a sample, it's another leap, I think, intellectually for us is what we're actually trying to do with statistics. We are using a subset of the population or a sample, and we're trying to say things about this broader population through inferential statistics. And so the term statistics specifically refers to a numerical measure about a sample, whereas a population, though in common language we may talk about statistics that way, really we would call that a parameter. That's something that we're trying to estimate with our statistics or with our data. Not that important for the exam, but do make sure that you can distinguish between those two concepts. Overall, and this is not just true of the exam, but for statistics in general, is 90% of the battle is picking the right tool for the job. So you've got two variables you want to compare, and you think about what is the level of measurement and what would be appropriate given those levels of measurement. And also, to some extent, what the directionality is in terms of what you think of as an independent variable, what you think is a dependent variable. That also can factor in. But it seems like you've all been able to figure that out for the most part. I want to mention that we're not going to cover the non-parametric statistics in the exam. You should know the fact that parametric statistics, which is what the bulk of what we were doing, does have distribution assumptions. The exception is that there will be some questions about the chi-square test, which is a non-parametric test. And the reason why that's non-parametric is that it's always with categorical variables. And so there really are no distribution assumptions about categories. So that's the one exception. So some of those parallels that you had to know for, I think it was week 3, between a t-test and the analog for a non-parametric test, you don't have to worry about that. I think we mentioned in the course that the reality is those like the Mann-Whitney U test, for example, it's used relatively infrequently. There are occasions where people should have used it, but if you look at the literature, it's just nice to have in your back pocket, knowing that if your data fails to meet certain distribution assumptions, you do have those options. You're never completely stuck. As long as you've got good measurement and good data, there's some way you can analyze it. Okay, so that I wanted to make clear so you don't have to go back and review all those parallels. Not that they aren't useful to know. Okay, and then moving on. Okay, you should understand the concept of a z-score or a standardized variable, and there aren't actual calculations in it in the exam. It is all, I should have mentioned that format. It's going to be like your quizzes. It's true, false, multiple choice. No actual calculation, and also I should mention no StatCrunch. Bye. after your independent project, you'll be done with StatCrunch. But yeah, there won't even be a reference to StatCrunch. You won't see the word StatCrunch. Hopefully you've come to develop to love it just a little bit. But you should know how to calculate a z-score, right? So you subtract the mean, divide by the standard deviation. And you might wonder, well, why am I doing that? Well, centering, it's actually a two-step process. One is you're centering the variable by subtracting the mean, so that the mean now becomes 0. So anything that's positive means it's above the mean, anything that's negative is below the mean. So that's kind of useful in itself, the centering part of a z statistic. And then expressing it in standard deviation units, it makes it even more useful, because then you can compare different variables that may have vastly different measurement scales and vastly different variability, and kind of make apples to apples comparisons in terms of how far from the mean you're going. Also, it's kind of underlying what we do when we get to looking at correlation coefficients, which is really a regression slope between two standardized variables. But that part you don't have to remember, but just kind of the concept of a z-score and why we do it. I'm not gonna, well, I will later. This is just the 5,000-foot view of what's on there. The central limit theorem, you should know what it says or why it's so awesome, because it allows us to do inferential statistics, even though population variables may not be normally distributed. The fact that when we take a series of sample means from a population, the distribution of those are normally distributed, and that allows us to do all the inferential statistics that we do. So it's a little bit of statistical magic, and I will show one slide on that one. Levels of measurement, you should know ordinal, categorical, nominal, ratio. But and I know it's sometimes difficult to remember the differences. The biggest one I think people struggle with is the ratio versus the interval. And just remember that ratio should have a meaningful 0 value. So I don't think that comes up on the exam, but that is, you should know in general the levels of measurement and review that. Variance and the standard deviation. Now, variance we don't often use in terms of reporting it as an actual statistics, but conceptually it's very important, because we're trying to explain the amount of variance in some of our statistics when we get to regression, when we have R squared, which is basically the proportion of the total variance that we explain. But what we normally report is the standard deviation, which is actually makes more sense than the variance. The variance is the square of the squared value of the average differences. And the reason we have to unsquare it for the standard deviation or take the square root is that we've done that so that everything's kind of going in the same direction. We've got the absolute value. When we take the square root and get the standard deviation, we're actually talking then about the average deviation from the mean. So you should be able to understand the difference between those two. And an ANOVA versus a t-test, obviously they're very similar. very similar applications. The big distinction being, and I would make this participation, but you can shout it out in your head if you want. ANOVA is for 3 or more groups, t-tests are for 2 groups. That's the main distinction to consider. Also, the fact that when we do an ANOVA, the null hypothesis is that the means of the different groups, 3 or more groups, are equal, and that we're not saying which, if we reject the null hypothesis, we're not making a specific comparison among any 2 of those. We're just saying that overall there is a difference in the means with ANOVA. T-test, you know, which just by the p-value alone, you can say whether there's a meaningful statistic, I should say a statistical difference between the 2 variables. Okay, the one you're probably most anxious about, because we haven't covered it as much and just are either still working on it or haven't had time to really process, is the correlation and regression. And some of you may not even gotten to the homework yet. So there is not a lot on regression. You should know that the 2 are related, and I will hint that you should know what OLS means in the context of regression, and that's the ordinary least squares. And ordinary just means typical. It's like what we usually do with regression. And the least squares refers to the fact that what we're doing when we do linear regression is find the best fitting line that minimizes the sum of squares, meaning it minimizes the variance. So basically we're fitting this line between a dependent variable and independent variable where it minimizes the distance from those points between the line. That's basically the extent of what you should think about for the linear regression. Okay, so that was the big view. So those 2 slides, that's pretty much the main things that you need to be considering. And now I'm going to go into a little more depth on some of these concepts. And there may be a few things that I didn't mention, but they're less important, perhaps. So you should be able to distinguish between an independent variable and a dependent variable. Even when we're running a t-test, even though we don't formally talk about it necessarily as an independent and a dependent variable, conceptually, we've got an outcome that we're interested in, which we call our dependent variable, and the independent variable are the things or thing that is the predictor of, or the things that are thought to influence the outcome. And so it's more of a conceptual distinction, but it also matters in terms of what we put as an outcome, even in the t-test as our dependent variable. So just be aware of these concepts, but we don't cover that much. Okay. Oh, sorry. I got those a little out of order. One more page of 50,000 foot view. You should know the difference between ANOVA and ANCOVA and their analysis of covariance. This comes up this week more than previously, which is that basically ANOVA is like ANOVA where you've thrown in a covariate or something to adjust for. Okay, so it's actually very similar to a multiple linear regression, where you've got a factor variable and then some sort of other continuous measure in there. We don't actually use ANCOVA much in the real world, but just conceptually, it's like one step extra in terms of ANOVA, adding some sort of control variable. But otherwise, they're very similar. Okay, oh, here's another one that people get confused. Type 1 error versus type 2 error. Oh. Very easy to confuse these. So just make sure that you've got these right. And here's a way to remember it. Type 1 error is also known as an alpha error, meaning let's say we pick an alpha p-value of 0.05 as our cut point, and we find something that's p equals 0.03, and we say, okay, we're going to reject the null hypothesis. in theory, we could do that just by chance alone, and it's not actually, there is no real difference. So a type 1 error has to do with the fact that we found something we think is statistically significant, but actually it's due to chance. And we expect those to happen about 5% of the time, right? The whole setup here, the whole game of statistics is that we're gonna be wrong 5% of the time, and we're willing to live with that. So type 1 error is just that first kind of, hey, we took our chances. we lost that one time. Okay, so that's an alpha error or type 1 error. Type 2 error is, you can think of as a beta error. So the order 1, 2, alpha, beta. Type 2 error has to do with a lack of power. So we basically fail to detect the difference when it actually exists. So we just didn't have, maybe we didn't have a big enough sample size, and it just, yeah, there's a difference, but we weren't able to detect it at that level. And so if we had increased our sample, maybe if we did it, again, we would find a difference. So it's failure to detect a difference, a failure to reject the null hypothesis. So do what you got to do to memorize that one. I admit that I always have to use some sort of mnemonic device where I'm like, okay, this is a type 1 error, this is a type 2 error. Very easy to confuse those. Okay, but yeah, so if you think of them as alpha beta, that makes it at least easier for me. I don't know what works for you. So also 1 sample versus 2 sample t-tests, they're very different, really. One is about comparing to a population, a known population value, and you're saying, hey, is my population different? You only have 1 sample in your data, most likely in that case. A 2 sample t-test is when we have 2 samples, usually within our own study, where we want to know if they're different. So 1 sample based on a known population parameter, or a known population's value, and a 2 sample where in both cases, we're trying to estimate some population parameters. I already mentioned independent versus dependent. The 2 corrections for a chi-square test, the Fisher exact test for when you get really small cell expected cell counts below 5, and the Yates correction for when you have cell counts less than 10. That's relatively recent in terms of homework, but do remember those 2. And the reason why that's important, actually is important, is that when you run a chi-square test, it is fairly often that you will have a cell, especially when you start getting like into 3x4 tables, or well, even in a 2x2 table, I'm sorry, where you would do these corrections. It happens fairly often. And so you want to make sure that you're actually reporting the right p-value, because often if you do the default settings in statistics, I'm sorry, in a stats program, if you're not careful, you could report the wrong p-value and say it's statistically significant. So the Yates correction and the Fisher exact test correction are important to know, and actually do come up in day-to-day statistical practice. Okay, and then I mentioned OLS. What does it mean in linear regression? So just basically know what OLS stands for and what it means. Okay, so back to the right order here. Continuous variable, those are the ones that we use often in linear regression and correlation. And in theory, they can take on an infinite number of values between 2 points. So even though we measure things like height and weight, usually in inches, theoretically, there are fractions of inches, or microfractions of inches. So time is another one that would be a continuous measure. So remember the other ones, nominal. One way to think of that name, nominal, is actually what it means. Ordinal, ordered categories. Interval, that's where we don't really have fractional values of whatever it is we're measuring. And then ratio is when there's a true 0. Here, this little table helps with the classification. I'm sorry, the differences. So nominal is purely a classification. So sex, race, ethnicity, religion, things that have no ordering. Ordinal could be thought of as categorical in some ways, in that you may have names for it. So like self-reported health could be fair, poor, excellent, very good, etc. But that actually has an ordering to it, and you could actually think of it in terms of having some magnitude. What distinguishes it from the higher levels is that you can't say what the difference is between the distances. You can just say the rank order of those things. Interval, something like a true rank, counts, those kinds of things are interval, and then ratio has a true zero. That's the main thing to distinguish it from interval. And in practice, we don't really distinguish between interval and ratio variables when we're doing statistics in terms of the types of tests that we use. So frankly, I don't know why we spend so much time on this issue in textbooks and in the scores, but it's out there. Okay. As I mentioned, so again, I've already gone over a lot of this stuff, but now I'm going to hopefully touch on these things in slightly more depth. So descriptive statistics, when we're doing descriptive statistics, we're actually doing things about a sample. Okay, so when we calculate a sample mean or a sample standard deviation, those are for the sample, and we can use those to describe what's happening in our study sample, but ultimately that doesn't get us very far, and we are going to want to do some inferences to a larger population. Okay, I'm going to move my screens right where I need to be. Okay, central tendency indices, median, mode, and mean. You should know the differences among those. The mode being the highest frequency. The mode is not very useful. The only thing I can think of as an example of where the mode would become useful is like, what is the typical age that teenagers start drinking alcohol? Okay, so I don't know, maybe it's 16 or something like that. I don't know. I guess it depends where you live. But for people who do initiate, what's the typical age that a child will, and obviously legally it's 21, but in reality, what's the average age that someone starts consuming alcohol? And that could have value, because if you're trying to plan an intervention, you're like, okay, well, what year should we bring in the DARE officers to the school? Well, we'll do it our sophomore year, because all the kids start drinking their junior year, or something like that. In which case the mean might be, I don't know, 19, 20, 21, or something like that. But the mode would be the most common value. So that can have some applications in some settings, but most often not. The median is useful whenever our distribution is not normal or has outlying values. The median is less susceptible to some of those effects of outliers. And it's, you often hear things like median household income and median housing price. And the reason is that you've got these really extreme folks who have really big houses or really big incomes, and then there's the rest of us. And so if you report the average, it gets, off quite a bit. That's why you hear those reported so often, even before you took this course. The mean, you should know that that is simply the arithmetic average. You sum up the values divided by the sample size, and you're good to go. All right, note that those three measures of central tendency will all be equal in a purely theoretical perfect normal distribution. They'll sit right at the center of that distribution. In real world, most distributions are a little bit off. However, on the exam, we will not talk about skewedness, kurtosis, all that stuff. Yay. That's another one that's like, it's like taking your medicine in statistics. Gotta learn that stuff, but it only comes up ever so often. And there's little transformations you can do to make your data more normal, which we don't get into here. But all right, so the overall concept of variability. So means, medians, modes, those are a description. of what a typical value is. Variability as a concept is how spread out is the data. And there's different ways that we can report variability, which is different from variance. Variability is just the spread. So we can do the range, we can do the interquartile range, standard deviation, and variance. Most typically, we're reporting standard deviations because we're using means, but if we are reporting the median, we're going to want to do the interquartile range. So you should know what the interquartile range is. It's the second and third quartiles, those middle two quartiles surrounding the median. Range is just the difference between the maximum and the minimum value. All right. I'm not going to go into the detail on the variance, but just know what the variance is. Standard scores, as I mentioned, also called a z-score, and it is calculated by taking the mean and subtracting that from all the values and dividing by the standard deviation. Okay, so in this example we have here, we had a value of 100 for the one person. We know the standard deviation, I'm sorry, the mean was 100, the standard deviation was 25. The value that we had for that person was 125. So their score would be 1.0, which means that they are actually one standard deviation above the mean, which you can see 125 is 25 points higher than the mean. So that's, and then this next observation at 50, it's 2 standard deviations below the mean. So it's pretty useful for that purpose, and that's why we do it. It's kind of like, you know, we talk about things in dozens instead of single units. So how many dozen things? So when we divide by some value like the standard deviation, it's just changing the units. It's really not doing anything to the variable itself. And if you were to run a correlation between a standardized variable and itself, it would be perfectly correlated. So you're not like doing black magic on the original variable. All right, correlation coefficients go from -1 through 1. And a 0 means no correlation. So minus sign means it's negative correlation, positive sign, positive correlation. The absolute value of those is what tells you the strength. Don't get that confused. Negative 7.5 is just as strong as positive 0.75. Okay. These rules are not written in stone anywhere, but generally we would say that certainly 1 is a perfectly positive correlation. If, in that case, you're probably measuring exactly the same thing. You're not going to find too many variables that are actually correlated 1.0, but theoretically, you could have two truly independent measures and they could be correlated that highly. But 0.7 is when we started to get a strong relationship in either direction, negative 0.7 or positive 0.7. 0.35 we would say is really our minimum cutoff for saying that things are correlated, but in that case it would be a weak correlation. Anything below 0.35 we would either say no correlation or very, very weak correlation. Okay. And it's hard for you to see these lines possibly, but you could see a purely negative value or negative correlation of 1 would look like this. So as 1 is going up on its axis, so as we go our higher values of x, y is actually coming down. That's a perfect negative correlation. A nearly perfect, but strong positive correlation here. You can see as x is going up, as y is going up, they're going up that way. A weak negative, and then no correlation will look like a scatter of dots. You will not be asked to interpret a graph, so just conceptually that'll help reinforce. Okay, I'm going to skip that one. Inferential statistics. So after we've done our little calculations of means, medians, standard deviations, min, max, all that, what we're really trying to do with our data often is infer something about a population. So we're taking a sample There are certain assumptions about that it's a random sample, that it's representative of the population from which it was drawn, et cetera. But we're using statistics to say what is probably true in the population as a whole. So if we're testing a drug against a placebo, we're not testing it on everyone in the population, we're testing it among a sample or a subset. And we're saying, okay, well, if we have a big enough sample size, what's the, and we see a difference, what's the likelihood that this difference is due to chance? That's what we're doing with inferential statistics. Okay, so drug companies kind of abuse this a little bit, honestly, where they'll pick, even a very small difference can be statistically significant if you get a big enough sample. So it used to be the drug trials were done on relatively small samples, 50 people versus 50, 50 with the new drug, 50 in the placebo. And, you'd have to have a pretty strong effect for it to be statistically significant. Now what's happening, and I'm sorry, I'm like soapboxing during the middle of the review session, but what's happening now is that if you get big enough samples, even a very, 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 very small difference, a non-zero difference could be statistically significant. It doesn't have any clinical difference, it's not clinically meaningful. Okay, but that's just something to keep in mind, that statistical significance does not mean medical significance necessarily. Okay, back to the central limit theorem. Notice there's a star here. It's a really important concept. It's not something you think about that often when you're actually doing statistics, but it's kind of like back there making the whole thing work. If it weren't for this, we wouldn't be able to do a lot of this. You'd be like, oh, that'd be nice, but it exists. The central limit theorem, it's a mathematical statement or formulation that says that the mean of a sampling distribution of the mean always equals the population mean. More importantly, that as you get larger and larger samples, the sampling distribution of those means. So I take one sample, plot that mean, take another sample, plot that mean. That distribution will be normal. And that's what allows us to do things like t-tests and other tests, which are ultimately based on means. It has to do with the fact that if we took repeated samples, that distribution would be normal. Okay, I'm going to skip that because it doesn't come up. Just keep in mind that parameter estimation means that we are estimating with our data, with our sample, some unknown statistic. So a good example would be, especially in public health, how many people have asthma? 10%? 20%? It's good to know, because for planning purposes and for just kind of run-of-the-mill day-to-day epidemiology, when we're trying to get a handle on what's happening in the population, we want to take a sample and figure out what's happening. What percentage of the population, for example, has received the COVID vaccine? That is probably based on sampling techniques, not based on an actual pure count. It's probably based on a very, very large sample, but it's not like everyone has been individually checked to see if they had the vaccination. So, but that's maybe a poor example because we probably have close to the population measure. But let's say we want to know what percentage of the population has depression. We'll probably use some sort of representative survey, and that would be the way that we would obtain that information. It might not be perfect, but it's our best way. And so we're trying to estimate what is that parameter. And it could be either a point estimate, such as 40%, or it could be an interval. So when we calculate confidence intervals, we say, well, somewhere between 35 and 45% of the population. And that's actually more informative than presenting an actual number, because it's more accurate in some ways. It's really easy to get hung up on, oh, well, 43% of Americans have such and such. Well, the estimate is probably somewhere in a range of 40 to 45%. And so that's really a more valid way of reporting things anyway. Okay. Okay, so I talked about confidence intervals. You should know, the concept of a confidence interval. You don't have to calculate a confidence interval. But when we calculate a confidence interval, we're saying that within these bounds, within this lower confidence limit and this upper confidence limit, that is where the likely population parameter falls that we're trying to estimate. So if it's, and it could be something like a difference between two means. What is the confidence interval around that difference? Well, this is where the true difference is likely to lie. Okay. And if it's just a simple statistic like a mean, we also know that our sample may not be perfectly accurate as far as what's happening in the population. So we put some confidence intervals around it. Okay, back to the null hypothesis. I was hoping that this review would make it seem like it was not overwhelming, and I'm like, oh gosh, okay, here we go, back to the null hypothesis. The null hypothesis is, again, the main thing to remember with that is that the variables are not associated, that they're not related, and that's counterintuitive. But the reason we're setting it up that way is because we're actually interested in the opposite of that. We're often interested in the fact that there is a difference. But the way we formally set up the statistical test is to say that there's no difference. And if we reject the null hypothesis, then we say, hey, there is a difference. And that would be our alternative hypothesis. Okay. So obviously we wouldn't do a study to show that cigarette smoking is unrelated to lung cancer. We would set up a study to show that to test whether there is an association between cigarette and smoking. But the null hypothesis would say there isn't. Okay. Most studies are looking for an association. It's rare that we would set up something specifically to show no difference. The only exception would be getting back to the drug trials things. If we could have a lower cost formula and show that it has the same effect as another drug that's maybe more expensive or maybe has, some other limitation on it, we might try to show equivalence that way, but that's pretty rare. Usually we're looking for a difference. And usually it's in our heads, it's in a specific direction. Most of the time we end up doing two-tail tests. Although that's another way that drug companies budget. Okay. Okay, research hypotheses. So yeah, the null hypothesis, some of you in your writing would say, my hypothesis was this. That wasn't your hypothesis, that was the null hypothesis. Your hypothesis was actually something interesting, which is that there's a difference. So do refrain from saying, my hypothesis is that there's no difference. It's the null hypothesis you're testing. Your hypothesis is more important, but that's not what we're testing. It's statistics. Okay, I made the analogy with the criminal justice system. If that helps, innocent before proven guilty, maybe that'll help. Think about that. I'm gonna stop at that. Okay, and so when we're setting up these tests, a type 1 error is when we, let me make sure I got this 2x2 table right in my own mind. Oh gosh, this table's not helping me. I'm gonna just go past this. Sorry. I'm afraid it's gonna make me and you more confused. Okay, but a type 1 is a false positive. Okay, that means that we rejected the null hypothesis. We were sure that that p-value meant something, and like, oh, it's 0.03. Well, it turns out it's not true. Now we wouldn't know this, right? We wouldn't know that there's no association in reality, but we're allowing for that possibility, which would be a type 1 error. And it could be that we could discover that when we do repeated studies of the same phenomenon, and we're never able to replicate it ever again. And we might say, okay, but we don't actually know that we made the error. Okay, this is a theoretical concern. And same with the type 2 error. Okay, so we fail to reject the null hypothesis. turns out there was a difference. So if we did a really crummy study and it was really small and we didn't measure things well, and our p-value was 0.45, turns out if we had measured it appropriately and had a big enough sample, we would have found a difference, but we failed to detect it. So that would be a type 2 error, false negative finding. Okay? And that does happen where there's so much noise in our measurement, or there's something else that we did poorly, where we just fail to detect it. And people tend to conclude, well, that's not worth looking at that anymore. And so that's why it's really important when evaluating a research study that you consider things like the study design and how did they measure it, and those kinds of things. It's not all about the statistical test. It's not, you shouldn't get overly excited about having a positive P or a significant p-value. Likewise, you shouldn't get overly discouraged if your p-value is not positive. If there's a slight signal, let's say your p-value is 0.06, and you had a small sample, it might be worth replicating that experiment again in a bigger, better designed study. So this is not, these p-values and the decisions we make based on p-values are not, the absolute truth. There are ways to make decisions about data and our findings. Okay, p-values. For a p-value less than 0.05, and don't forget the 0.05 cutout is a somewhat arbitrary decision that we've made as a scientific community to say this is the level of chance that we're willing to take to being wrong. So 0.05 is usually the cut point. Sometimes 0.01 is used, especially for larger sampled studies. And as we get into the realm of big data, we're going to maybe start to see a shift towards smaller p-values for statistical significance. That's kind of a new shift, so don't worry about that right now. But if you think about it, when we've got billions of records, you're probably going to get a lot of p-values less than 0.05, and so that's something to consider. But this is more in the context of like experimental design and smaller traditional studies. Okay, so a p-value less than 0.05, we say we reject the null hypothesis, and we say the null hypothesis is not very likely to be true. In fact, it has less than a 5% chance of being true. That's what we're saying when we reject the null hypothesis. And so a p-value of 0.001 is like, wow, it's really, really, really not likely that there's no difference. The null hypothesis is really not likely to be true. For p-values greater than 0.05, we don't have enough evidence to reject the null hypothesis. It's possible it's true, but we just simply didn't have enough evidence in our study. Okay. And as I mentioned, if you have a p-value that's kind of close, some people are like, well, you will see in the literature borderline significant. It's like when it's 0.06. That's acceptable to do sometimes. Ideally, you wouldn't report a p-value of 0.06 as being significant. However, as a side note, in a study, let's say you had a regression model and you found an association that was, p equals 0.06, you may mention it in passing, say, hey, this might be something worth looking at in the future, but you would not come to any kind of conclusions based on that marginal p-value. Probably shouldn't have confused you with that, but again, the point is these are somewhat arbitrary decisions we make. Okay, critical regions. So all of these tests that we do, the z-test, t-test, chi-square test, there's always a portion of that distribution that we call the critical region, where it's a part of a probability distribution, where if it's higher than that critical value, then we say that it is significant, and we reject the null hypothesis. And it's really easy to get these two things confused, the p-value and the critical value. So the value you calculate is higher than the critical value, it means your p-value is actually very low, or relatively low. It's below 0.05. And so those kinds of things, that logic is kind of sometimes catching some of you, I notice, in the homework exercises. Okay, so the t-statistic is, I'm sorry, the test statistic is not the same thing as a p-value. It has to do with the area under a curve and how much, and it's different across the different distributions. So a z-score value of 1.96 is not the same thing as a t-score of 1.96, and it's not the same as a chi-square test of 1.96. That's why we have the different table, the lookup tables for the different critical regions of the different tests. Don't worry about that too much because that's something from the exam. But one sample t-test, again, we're comparing a known population mean to some subsample. Okay, so we have some specific value that's already known, and we have one unknown parameter, which is our one unknown, which is our sample, one sample. Okay, statistical significance. When the null hypothesis is rejected, then we say it's statistically significant. That does not mean it's clinically significant. It doesn't mean it's even relevant, but it is statistically significant. It means that it's very likely to not be by chance. If the null hypothesis is retained, or when we say we fail to reject the null hypothesis, the results are statistically not significant or non-significant. Okay, and this just restates what I just said, which is that it's likely to be real, and it is not merely due to chance. It does not, however, say anything about clinical importance or meaning. Parametric tests, again, are the bulk of what we do in statistics, and that involves estimating a population parameter. It assumes some sort of distributional assumptions. Okay. Non-parametric, you don't have to know what any of those non-parametric tests are, other than the chi-square tests. Two sample t-tests. Okay, we always have two groups, and there's one independent variable that we're trying. I'm sorry, one dependent variable that we're trying to test. So our independent variable is actually the group, right? It's just a nominal variable. So it could be treatment X versus placebo. That is our independent variable. And our dependent variable is that continuous measure that we're comparing the two groups and we're calculating means. Okay, so experimental versus control, men versus women, children without having a disease. And the original t-test really was more for experimental conditions. We use it sometimes for these subgroup analysis, men versus women, children, has disease, not disease. Ideally, we would use this more strictly for experimental designs, but anytime we have two groups, we can use a t-test. But remember that with the t-test, we ideally also have similar sample sizes. You don't have like 10 of one group and 1,000 of another group. You will still see people use t-tests in those situations, but that really isn't what it was designed for. It was more for experimental designs, but you don't have to know that for the exam. Okay, again, one thing to remember, if you've got a continuous variable, two groups, you're looking at a t-test. And the null hypothesis, as it always is, but in the case of a t-test, is that the independent variable and the dependent variable are not related, and more specifically that the mean for the one group is the same as the mean in the other group, or you could say that the difference between those two groups is 0. Either way you look at it, it's basically saying that there's no association or there's no difference. The alternative hypothesis in a t-test is that the two group means are different. Doesn't say how different they are. It's only that they are different, that they are not 0. That's something important to keep in mind too. And I think when we say statistically significant, it tends to make you think, wow, it must be a really big difference. All it's saying is it's a non-zero difference. So the mean of group 1 and mean of group 2 are not equal. And we can report out what the difference is, the observed difference, and usually some sort of confidence interval around that. Okay. So the most common one we use is the independent groups t-test. And that's when we have two groups and we want to compare their means. We just went through that one. There are some variants though, such as paired t-tests. This is when we might be using the same group twice, or there's some other dependency between two groups. So pre-test, post-test, we might look at something like BMI at baseline, you do some kind of intervention and then test the same subjects to see what their BMI is after the intervention. Because there's that dependency, our statistics have to account for that dependency. So if you recall, with the independent t-test and for a lot of statistics, there's an assumption of independence. So if you are doing repeated measures, it needs slightly different mathematics behind it to get the right p-value. Slightly more complicated in terms of dependency in groups. You wouldn't, for example, want to sample two people from the same household. So this comes up sometimes in research where a household is selected to participate and other members of the same household want to participate, especially if there's like an incentive to participate. And as a researcher or as someone working on the study, you would be, no, we unfortunately can't do that, and that's for statistical reasons. We need our observations to be independent of one another. Okay, so dependent group t-test is whenever there is a known clustering of the observations. But normally this is something that's planned in advance, where we're saying, okay, we're going to study the same subjects twice. Okay, ANOVA, 3 or more groups, very similar to a t-test. Something to emphasize here is that there still are only 2 variables in an ANOVA. It is not a 3-variable test or a 4-variable test. The 2 variables are the dependent variable, which is a continuous measure, and the independent variable has 3 or more categories. It's still only 2 variables. So do remember that. Okay. Yes, and just like the t-test, the dependent variable in an ANOVA is either interval or ratio scale. The independent variable is nominal or categorical. It could potentially be ordinal, something like normal weight, overweight, obese, but there's some sort of discrete groupings. The null hypothesis is very similar to a t-test, but it's really important to know that it doesn't say which groups are different. It's basically saying group 1 is equal to group 2, which is equal to group 3, which is equal to group 4, or however many groups you have. And then the alternative hypothesis in ANOVA is that at least one of those group means is different. It could be multiple or different, it turns out. But what you're formally testing is that one of those group means is not like the other. Very similar assumption that you have for a t-test. Random sampling, dependent variable is normally distributed. Okay. I'm going to skip over that. Repeated measures is similar to a paired t-test. In this case, we're extending that to 3 or more measurements. So paired t-test pre-post, same concept, but this would be if we had, let's say, baseline, 1 year of follow-up, 2 years of follow-up, and so on. And this is actually increasingly done in research, where we don't want to pre-test, post-test designs have a lot of problems because there's a phenomenon called regression to the mean, and there's ceiling floor effects, which we don't go in this course. But a pre-test, post-test design, there's a whole bunch of reasons why that's not a great design. But for something where you have multiple points, repeated measures, where you can look at trajectories over time, they are preferred. The problem is they tend to be more costly study designs. because you have to take that many more measurements. But you get a lot of statistical bang for your buck by doing repeated measures. Okay, and then I'm going to skip that. Interpreting your p-value. Oh, I think I already did that. So for small p-values, we reject the null hypothesis. Okay, parametric, non-parametric. Sorry, I didn't rehearse this. This is I made the slide deck, but I did not rehearse this review. Okay, don't need that. Chi-square test of independence. Chi-square tests are really useful. I use chi-square tests all the time. It's basically, especially in epidemiology, where we're often looking at a disease, like a disease exposure relationship. And so we know we have a group that's exposed, yes, no. We have a group, have a disease of interest, yes, no. Set up a 2x2 table. There's all kinds of things we can do with it. But the main thing we want to know is it statistically significant? The differences that we observe. And it's really easy. You can calculate odds ratios and relative risks and other things from a 2x2 table. But basically, it's a test of proportions of, are they different between the two groups? So is one group disproportionately exposed versus another group? Or does one group, based on their exposure status, are they disproportionately likely to have the disease? Those kinds of associations. So Pearson's chi-square tests are really fundamental to work in epidemiology, where that's often how we measure things. In clinical settings, it can also be pretty important. So some assumptions of the chi-square test, or some characteristics. The null hypothesis is that the proportions across the groups are equal. And again, I mentioned a 2x2 table, but this could be true of a 3x4 table or any number of configurations of a categorical data. Okay, and we're basically saying with the null hypothesis that there are no differences in the proportions across these different groups. The alternative hypothesis, which is kind of similar to the ANOVA alternative hypothesis, which is that there's some difference somewhere in that matrix of cells. So it's really easy to eyeball that and say, okay, well, that percentage is different than that percentage, and so that is what's statistically significant. That is not actually what is being stated by the p-value from a chi-square test. It's just saying that there are differences in the proportions in the groups. You don't want to say, well, we found that this particular proportion is different. Now, one exception is a 2x2 table because there's only one possible comparison to make there. But for anything greater than a 2x2 table, you're not really saying specifically what's different among the proportions. Similar assumptions to a lot of these other things: random sampling, independence, and then this other little add-on, which is that the expected frequency must be greater than 0 in a cell. That won't be on the exam, but what will be on the exam, I'll just tell you right now, Fisher's exact test and Yates correction. Again, you might wonder why this little detail seems kind of trivial considering some of the other things, but it's something that actually does come up. So if an expected value for multiple cells is less than 5, we use the Fisher's exact test. And in normal statistical output, it'll just be reported out there. In the case of StatCrunch, I think you have to ask for it. But in any case, Fisher's exact test is what we would use. And then for Yates correction, this would be for where there's an expected count of less than 10. Okay, Pearson's R. We introduced correlation pretty early in this course, and then it comes up again in the context of regression. Pearson's R, that's the same thing as a correlation coefficient for 2 variables. And Pearson's R is what we were talking about earlier with correlation coefficient, -1 being purely negative correlation, 1.0 being a perfectly positive correlation. You can also run a test on that, you can use it for statistical inferences. It's not strictly a descriptive statistic. And so you can do a formal test to see if that correlation is statistically significant. That doesn't alter our interpretation of the strength of association, but it does tell us whether it could have been done, we could have found that strength of association just by chance alone versus not. And usually that's purely a function of the sample size. If you have a positive correlation of 0.8 and it's not statistically significant, you have a very small sample. And so there's a pretty strong relationship between sample size and the likelihood of finding a significant correlation. Again, though, just conceptually, I think it's important to know that the null hypothesis for any test is that there's no relationship. In this case, the test would be, the null hypothesis would be that the correlation coefficient is 0. And don't forget that the correlation coefficient of 0 does mean no correlation. -1 means strong negative correlation, +1 means strong positive, but 0 again. So the null hypothesis of an R related to an Pearson's correlation, we just let StatCrunch tell us whether, or our stats program, whether it's statistically significant. Okay, we're getting there. We're getting real close to the end here. So in the context of linear regression, R squared, which is something that we can obtain when we run a regression model. And this could be with multiple variables. So we have our dependent variable, we can have multiple independent variables. R squared is a really powerful tool that allows us to say how much have we explained with the variables that we've chosen to explain. And one of the goals that we have in linear regression is to add variables that are going to increase our R square value, meaning we're explaining more and more of that, the variability that exists in that variable. So if we can explain something like 30%, if we can R square 0.30, we're explaining 30% of the variability in some phenomenon. So our criteria for R square usually are that if we can explain more than 10%, our model's doing an okay job. If we can explain 30%, it's really doing a lot. And then we start to get, if we can get more than that, great. But we never expect to explain the entire phenomenon of interest. So for example, height, like, gosh, what goes into height for a human? There's genetic factors, probably. There's probably diet. There's probably, and I'm sure you could find something that was perfectly correlated, like parent height, okay? But then the question, well, what determines the parent's height? So you can cheat a little bit and put variables that are basically the same thing as the outcome, and you can improve your R square. But usually you want things that are truly independent predictors of the, and you're not basically measuring the same thing twice. But that's a whole nother level. But once you've gotten to correlate to regression, it's really a powerful tool, and it's what's used in all kinds of fields outside of healthcare, outside of epidemiology, outside of academics in general, where people use models to try to predict some outcome of interest. And you can add you can add nominal variables, you can add continuous variables, you can add all the different levels of measurement into these models, and your goal is to increase R squared. So that's not a huge part of the exam. In fact, I'm not sure, but I just wanted to, since we haven't really talked about where all this is headed, regression models are very powerful, and if you can run regression models, you really are doing the heavy lifting in statistics. We don't cover logistic regression in this course, but that's a similar concept, which is where we have a dichotomous outcome. So we want to predict disease, yes versus no. 90% of what I do in my day-to-day statistical work would be linear regression or logistic regression. Those come up the most often. So you guys made it almost to the almost to the farthest point. There are other things obviously more complicated. Survival analysis is another thing that sometimes is covered, but all right, so that is about it. The least squares regression, again, the least squares line is the best fitting line. And so that line, which is computed mathematically, which minimizes the difference between the line and the different points, is our OLS regression line. Okay, I think I already covered ANCOVA. Okay, so that is my review. That applause story is just that it's over, right? We made it, yay. No, I have to say, I am super impressed with the quality of work that has been done in this class by you all. It's been really amazing. I've taught undergrads before, not online, and I feel like you guys are getting it. Now, I could be wrong, we'll see how it goes on the exam. No, it'll be fine. If you've done fine on the previous exams, you'll do fine on this. It's open note, open book, open everything. Obviously for the final, you should work independently. But if you need clarification on a question, like the wording on a question, please just ask me. I will, if it seems appropriate, I will post to the group any questions for clarification. The only trick with that is that some people are going to do it at different times, and they might be bummed out if they didn't hear that. So hopefully I'll ask those questions early rather than late, but hopefully that won't be a stumbling block. The wording should be clear, but you're welcome to ask me questions about anything during the exam. That's very good too. Okay, so switching gears, we are over time. Sorry about that. It took me a long time to get through that. But so that slide set is available for you on Blackboard, and that'll spare you from having to go through other notes from other weeks, and you can then use that as a while you're taking the exam if you want. So any other questions about other things? All right, well, it's been my pleasure to, I'm sorry, I should always look in the chat. Oh my gosh, you'd think I know that by now. Let's see. There's a chat. Oh, thanks. Yeah, thank you. What a nice surprise. Thank you, Paul, for your cooperation in this course. I'm being sincere. I'm really impressed with how you all have managed to do this content in 4 weeks. I couldn't get my students to get some of this in 10 weeks sometimes. So you guys did this in 4 weeks. Not bad. And I hope you've developed at least some appreciation for statistics, if only to say, hey, these aren't perfect, so I'm gonna use my own judgment when I look at research studies. And that's really an important lesson from all of this, is that this is a tool. It's our best tool, and you know, it's also self-correcting, and that if you present a result that's false, that there's going to be somebody else who's going to do the same study and find a different result. So it does correct itself over time. But it is important for understanding that no one study is definitive. So one study that shows a relationship between a variable and an outcome, that is not definitive. And this is why we need to build a body of evidence across different settings, different investigators, and that's how science works. And unfortunately, what happens is that the media and others will zoom in on one study and say, okay, this is definitive. And this is what happens with things like, oh gosh, like the whole anti-vax movement started from like these bad studies on vaccinations and autism, which were later shown to have no validity whatsoever. Even the investigator said, no, that wasn't right. But we can't undo, it's really hard to undo, like when the media reports on those things, we're like, it takes years sometimes to get back people's trust in science. And I can understand why. It does seem a little iffy, but all right, well, thanks again for taking your time. And just a quick reminder, if you could fill out course evals, that's always helpful. I know you've got lots of things and you want to be done, but if you could do the course evals before you finish. And you have till Sunday night, 12 p.m., no, 11:59 p.m. Sunday night to get everything in, including the final exam. So hopefully that's enough time. All right, well, thank you, everybody. Catch you later.
Professor.